Hello, my name is Connor Stone, and welcome back to the AstroPhot tutorial series. Today we have a slightly different tutorial on the books. Rather than going through the AstroPhot tutorial notebooks, we're going to take a step back and talk about coordinate systems as AstroPhot sees them. This is going to be important for some of the future tutorials that we'll get into, which involve fitting and multiple image analysis. Okay. Now, AstroPhot actually has a coordinates tutorial or web page on its website, and this gives you a basic rundown of how AstroPhot sees the coordinate systems in astronomy. There's essentially three systems you need to keep in mind. So the three coordinate systems are the world coordinates, the tangent plane, and the pixel coordinates. Let's do a quick rundown of these three. So the world coordinates, this is what you would say like RA dec, right? Ascension and declination. These are the coordinates on the celestial sphere. As far as astrophoto is concerned, these should always be in degrees. And these coordinates are where you're going to get something like catalog values for the position of an object. It'll probably be given to you in world coordinates because it's an object on the celestial sphere and we want to know where it is in the sky. But world coordinates are polar coordinates, which means that modeling or representing some sort of extended object in world coordinates is kind of terrifying. So AstroPhot does not use the world coordinates when it's doing its modeling. Instead, it uses the tangent plane. So the tangent plane, if you imagine the celestial sphere as a sphere, the tangent plane is a plane that contacts that sphere at a particular point. The tangent plane is a Cartesian grid, and that is where AstroPhot does its modeling. If I say, oh, I'm going to put a Sursic model on the sky, that Sursic distribution of light is represented in the tangent plane. This is nice because on that Cartesian grid, everything is linear. I can calculate distances between things, and it all works out correctly. Now, the celestial sphere is a sphere, and that's actually where things are on the sky. The tangent plane is a plane. Only at the contact point are the two coordinate systems the same. Same. Beyond that, technically there's a distortion between the tangent plane and the celestial sphere, but that distortion is fairly small as long as you don't make too large of an image. As far as astrophoto is concerned, units in the tangent plane should be in arcseconds. Finally, there's the pixel coordinate system. That's where your data lives. You collect your data, you get a grid of pixel values. Those pixel values are in pixel coordinates. So the pixel coordinates tell us where in the image we are. A coordinate of 0, 0 corresponds to the 0, 0 indexed pixel. Um, Keep in mind that FITS and AstroPhot use the indexing that in the same way as the coordinates. So the coordinate 5, 9 corresponds to the pixel at 5, 9 as far as AstroPhot is concerned. Whereas normally for NumPy and similar numerical packages in Python, they flip those coordinates. So normally if you wanted to access the 5, 9 pixel, you would actually enter 9, 5. That's really tedious. So actually, whenever you give AstroPhot an image, it's going to apply a transpose to that image automatically. But all of that is handled internally, so you don't have to worry about that transpose. When it gives an image back to you, it'll transpose it back. So you can work with NumPy the way you're used to working with it. It doesn't really matter for you, but internally, this is what AstroPhot does. Anyway, um, a step of 1 in pixel coordinates corresponds to a step of 1 pixel length in a given direction. So these are coordinates. You don't actually have to stick to integer movements of pixel coordinates. You can talk about fractions of a pixel by using intermediate coordinates, using decimal numbers. Okay, so those are the three coordinate systems. There's the celestial sphere, the tangent plane, and your pixel coordinates. AstroPhot has transformations between all of these. If you have an image object, you can just call the connecting function to map between the coordinates, and everything should work out just fine, assuming that you've got your world coordinate system injected into your image. Um, Now, each one of these coordinate systems needs to be connected to each other. Like I said, there's the like world to plane, world to pixel, pixel to plane, all of these coordinate transformations that AstroPhot can do. So there needs to be a system for translating between them. And essentially, the way that AstroPhot does this is with a mnemonic projection. That's the thing that converts a celestial sphere to a tangent plane. And it does this with three reference points, one for each coordinate system. So CR val is essentially an RA deck coordinate in the celestial sphere, and that gives AstroPhot the point at which the tangent plane touches the celestial sphere. Now, if you're going to do a multi-image analysis, it's important that the CR val for all of your images is the same number, because that means you're working with the same tangent plane for all of your images. If you if you have different CR vals for your different um, images, then in a sense you're working with tangent planes that are like crossing through each other. And so your coordinates don't necessarily make sense together. The second level is CR tan. So this is a reference point in the tangent plane coordinate system. Now, the way that AstroPhot handles this is the the CR val, the RA deck coordinates where the celestial sphere touches the tangent plane, that corresponds to 0, 0 in the tangent plane. So the origin of the tangent plane connects exactly with CR val. But you have an image, a grid of pixels, that isn't necessarily centered right on that 0, 0 in the tangent plane. So CR tan essentially is the contact point between your pixel coordinates and the tangent plane. Often it's just 0, 0. If you only have a single image, then it's going to be 0, 0 by default, and there's no reason to change that. But if you have multiple images in a multi-image analysis, you need to have a really clear picture of where these images are relative to each other. And so they each have an anchor point in the tangent plane coordinate system. Finally, there's CR pix. So this is the anchor point in the pixel coordinates. And CR pix is a coordinate in the pixel plane that corresponds directly to CR tan in the tangent plane. So you can think of the two as being like pinned together. And so if you have your if you have your pixel coordinates and the pixels are rotated because say your image wasn't aligned with north, where your telescope wasn't aligned with north when you took your image, if it's rotated, the CR pix and the CR tan, those are the pivot point in the two coordinate systems about which the rotation occurs. Those are sort of like the fixed point and everything else happens around it. If you change the pixel scale of your image, it's going to be scaling about that fixed point. So that's the spot where all the transformations happen around. So, as a recap, uh, the it can get complicated transferring between these coordinate systems, but just keep in mind in your head that CR val is in the world coordinate system and it connects to the origin of your tangent plane. CR tan is some point in your tangent plane and it connects to CR pix in your pixels. And essentially everything pivots around those contact points. This is all a little abstract right now because I've just explained it all in words. Let's go through a little demo that I created where you can actually see these things in action. In the demo, I've got a nice explanation of how everything works, and I talk a little bit about FITS header terminology. So CRVal is actually the keyword that's used in almost all FITS images to indicate that contact point of the celestial sphere for a tangent plane. it's very common to see tangent plane projections. CR-pix is that pixel coordinate connection. Now, CR-tan is actually an invention for AstroPhot because AstroPhot does a lot of modeling in the tangent plane. It needed an extra coordinate anchor point in order to do its multi-image analysis in a very concrete way. C-delt, or more commonly CD, is a matrix that encodes the linear transformation between pixel coordinates and tangent plane coordinates. Um, so the CD matrix is very useful for not just making that contact point, CR-pix to CR-tan, but actually the transformation, rotation, scaling, like your pixel scale, that's encoded in CD. And then C-type is an indicator that can tell readers what type of transformation is connecting these pixels to the tangent plane. So a key, something like RA tan SIP, means for the RA coordinate, we use a tangent plane projection and SIP distortions on top of that between the pixels and the tangent plane. We'll get into the SIP distortions in a second. Uh, I think XKCD is fun, so I included a whole bunch of different projections from XKCD, and there's some fun commentary in those. Okay, let's take a look at our three coordinate systems. Here we have a celestial sphere in blue. The observer, you, are at the center of the celestial sphere. You could think of that dot as Earth or something, or your observatory. And the celestial sphere is just essentially an infinitely far away sphere that represents the night sky. The sort of brown rectangle here, that is the tangent plane. So that tangent plane is connected at the red point. At the red point, the tangent plane connects. In principle, this tangent plane extends out infinitely. It's a Cartesian plane. And the way that you project a point from the celestial sphere to the tangent plane is to just make a line from the observer through the celestial sphere until it hits the tangent plane. And then this grid you see here, that's the pixels that your image is actually encoded in. And those can be rotated on the sky, they can shift around, but the main point is like they are on the tangent plane. They are in the tangent plane, but they may be distorted in the tangent plane. And so um, modeling makes the most sense in the tangent plane where everything is linear and a Gaussian blob is a round Gaussian blob. Inside your pixels, a round Gaussian blob might not actually look round. It might look elliptical if your pixels are stretched along a particular axis. So AstroPhot accounts for all of that in the way that it handles its modeling system, translating between these coordinate systems. Okay, so that gives you a visualization of like where all of these three coordinate systems live relative to each other. Let's talk a little bit for a second about converting between these coordinate systems. You shouldn't need these calculations, but it's just good to know. Like I said, to go from the world coordinates, the RA deck, to your tangent plane coordinates, you use a mnemonic projection. So the observer is at the center of the sphere. You got some point P1 that's on the world coordinate systems, and you want to figure out where that corresponds to the tangent plane. You just draw a line through them, and that line goes through the origin, the observer, through P1, and it lands at this point P, which is on the tangent plane. Point S, that is like the CR val. That's actually the contact point for the tangent plane onto the celestial sphere. This is the transformation between them. X and Y are the tangent plane coordinates. RA and dec are the celestial sphere coordinates. RA0 and dec0 are the CR val, like reference point on the world coordinate system. And this cos C is just an annoyingly long thing, so separated it out. Okay, so that's a nasty transformation, but it works. Plane to world is the inverse of this transformation, so that's how we get an RA deck given a tangent plane coordinate. It doesn't look nice, but again, it's all wrapped up, so you don't need to really think about it too much. Next, let's take a look at that. So here we have a little grid where the orange lines are the tangent plane coordinates. And the tangent plane is a very nice Euclidean grid. So nice, perfectly straight lines, perfectly perpendicular to each other. Um, that's our tangent plane grid in orange. And then in blue, this is what the celestial sphere coordinates are that have been mapped into our tangent plane. And you see, if we make the field of view really small, so essentially we're zooming in onto a small spot of the world coordinate system and the tangent plane, we're zooming right in. You can see that the blue lines that correspond to the world coordinates really do look like a nice regular grid right where um, we're doing our modeling. That's nice. But if we zoom out, if we start to imagine a really, really large image that we've taken with our telescope, very quickly you see distortions. Like look at the edge here. These RA deck coordinates are warped relative to our nice, simple tangent plane grid. So if you imagined trying to model some extended object in the night sky fully in the world coordinates, calculating distances between points would just be a huge pain, and it would be you'd have to use those really complicated equations above in order to calculate those distances. So if you have a large image, the tangent plane is not a good approximation. But if you have a small image, it's really, really easy to compute and very accurate representation of the world coordinates. There's another thing that can happen, which is why you really, really don't want to use world coordinates, which is um, what if your reference point where you pointed your telescope is near the poles? Well, then it gets really nasty. So here, let's zoom in. Here you can see, well now, the connection between our RA and deck coordinates and the tangent plane coordinates is just absolutely wild. There's nothing even close to a grid connecting these two. And you'll also see that it doesn't matter how much I zoom in anymore. When I'm near the poles, even if I zoom all the way in, it doesn't look like a nice regular grid anymore. The RA coordinates, the spacing between them is a function of declination. And so it doesn't matter if you zoom in infinitely far, and it doesn't need to just be the poles. You can go anywhere. Anywhere that isn't the equator, it doesn't matter if you infinitely zoom in, the RA coordinates are still squished to each other. And so a transformation of 1 arcsecond of RA is actually very rarely a translation of 1 arcsecond on the sky. Uh, that can be a pain for transformations. So that's another reason we use the tangent plane coordinate system to do all of the modeling and then map out of the tangent plane if we need to know world coordinates. Next, so that's the transformation between the celestial sphere and the tangent plane. Next, let's take a look at the connection between the pixels and the tangent plane. So the simplest transformation between the pixels and the tangent plane is with one of these CD matrices. So you have your pixel coordinates, U and V. I'm using U and V because I've basically just subtracted out CR pix from the IJ coordinates. You might as well just subtract that out because it's not very informative. So now we've got XY, our tangent plane coordinates, UV, our pixel coordinates, and a matrix that connects them. And if that's the only transformation in your images, then great. You can just invert the CD matrix to go the other way. And it's really easy to map back and forth between them. But real telescopes rarely are perfectly linear transformations between their pixels and a nice tangent plane on the sphere. So what's commonly used is SIP distortions or simple imaging polynomial, which creates a slight shift in the position of your pixels. The way that this is represented is actually quite clever. So you take your UV pixel coordinates and you add some function of the UV pixel coordinates. The like, yeah, the UV pixel coordinates has a perturbation function on it. And that function takes the form of a polynomial like this. The A and the B are coefficients, and then U and V are just raised to a given power to create the polynomial. And this transformation essentially says the pixel coordinate 5, 5 is not actually at 5, 5, it's at 5.01 or something like that, and then 5.11 or whatever. And then you do your CD matrix transformation from those distorted pixel coordinates into your tangent plane. Now, the reason this is clever is if you imagine, okay, I could do anything to go one way. I could do anything I wanted to add a perturbation going from pixels to the tangent plane. But what if I want to invert this? That's where things get a little complicated. And if you just take this equation and try to do a simple inversion, then you get something like this. Your pixel coordinates are a function of your tangent plane coordinates with the inverse CD matrix and this perturbation. It's negative now because we're undoing it, but this perturbation. The only problem is that this perturbation depends on the UV coordinates. If it weren't for that, then this would be really, really trivial to invert. So in practice, you've got a couple options. One is to do a root finding algorithm. You come up with some estimate that is just the linear inversion of your pixel coordinates, some estimate for UV, and then you do a root finding algorithm that figures out the appropriate UV um, coordinates, which satisfies this equation. It's really fast to do because this, for small distortions, is usually a quite accurate initial position. Another option is to take these UV coordinates, or these capital UV coordinates, which are sort of like the intermediate transformation, and come up with a new set of SIP polynomials. These are indicated with AP rather than A and BP rather than B. And these new SIP polynomials handle the inverse transformation. And if you've got a set of these, then you can really easily, just with evaluating some polynomials, translate between your pixel coordinates and your tangent plane coordinates. Let's take an exaggerated look at what that looks like. So here we've got our nice regular tangent plane grid, like usual, but we've taken our pixels, which are indexed as a nice pixel grid, 0, 0, 0, 1, 0, 2, 0, 3. But we know that those pixels were sampled after all of the optical distortions and slight perturbations that happen inside our telescope. And so we take that nice even pixel grid, project it onto where all those pixels actually landed on the sky, and we can get something like this. I've exaggerated it a lot, but you can see how now the individual SIP coefficients apply transformations to these pixels, and they sort of add some conversion for where the pixels end up in the night sky. The linear transformation component is easy. The CD matrix mostly just encodes a rotation and a pixel scale, which tells us like how big is our image on the sky. But AstroPhot encodes these transformations. So now you've got your grid of data, you put a model in the tangent plane, and it will integrate inside each one of these pixels to figure out how much flux should have ended up in that pixel. And it matters because some of the pixels are distorted and they become smaller. So they should become dimmer, but not because your model is dimmer, but just because the pixel itself represents a smaller area on the sky. AstroPhot is able to handle that if that is relevant for your images. Alternatively, in a lot of cases, you can just use AstroPy, and it actually has pixel to world and world to pixel functions that you can use. AstroPy doesn't focus much on the tangent plane. AstroPhot really heavily takes advantage of the tangent plane because of the fact that it's doing a lot of modeling. But if you're just trying to connect a position on your pixels to a world coordinate so that you can build up a survey catalog, then AstroPy is certainly everything you need. Um, all right. So that covers the world coordinate transformations in AstroPhot. You now know about the world coordinates, the tangent plane, and the pixel coordinates. You know about how the CR-val, CR-tan, and CR-pix are the pinpoints that connect these different coordinate systems. And we did a run through of the actual calculations that transfer between all of these, but for the most part, you shouldn't need to actually worry about those because they're encoded either in AstroPhot or in AstroPy, and they'll handle the transformations between the coordinate systems. I hope that you have an understanding of when it's appropriate to use each coordinate system, and you can carry on this understanding for our future tutorials where we're going to start to get into some of the more complicated analysis that you can do with AstroPhot, where you're hopping between images and sharing information in order to do your modeling. I hope to see you at the next video. Definitely ask me any questions that you have. You can contact me pretty easily. My contact information is on the AstroPhot website. And with that, I'll see you later. Bye.